You think Einstein had all the answers, don't you? The smartest man who ever lived, the one who figured out relativity, who understood space and time better than anyone. Sure, he did all that, but there was a question he couldn't answer. And it wasn't because he wasn't smart enough. It was because nature itself seems to have built a wall there, a place where our usual ways of understanding just stop working. Let me tell you what the question was. It's simple to ask. Why are the electric force and the gravitational force so different in strength? Not just a little different, enormously, absurdly different. Take two electrons sitting near each other. The electrical repulsion between them is about 10 to the 42nd power, stronger than the gravitational attraction. That's 1 followed by 42 zeros. The gravity between them is so weak compared to electricity that it might as well not exist at all. Now, you might say, so what? Different forces have different strengths. But that's not the problem. The problem is that both forces have the exact same mathematical form. They both fall off as the inverse square of the distance. They both act between particles. They look like they're related, like they're two versions of the same thing. But one is incomprehensibly stronger than the other. Why? Einstein spent years trying to unify them, trying to find a deeper principle that would explain both. He failed. Here's what bothered him, and it should bother you too. Gravity works on everything. Every piece of matter, every particle, every atom pulls on every other atom with gravitational force. It's universal. There's no such thing as negative mass, no way to cancel it out. You just add up all the mass and you get the total gravitational pull. Simple. But electricity has two kinds of charge, positive and negative. They cancel each other out almost perfectly in normal matter. That's why you don't feel enormous electrical forces all the time. Think about that for a second. If electrical forces are so much stronger than gravity, why is gravity the force that dominates the universe? Why do planets orbit stars because of gravity, not electricity? The answer is that electrical charges balance out. A piece of rock has just as many positive charges as negative charges, all mixed together intimately. The net electrical force is essentially zero, but mass only comes in one kind, positive. It never cancels out. So even though gravity is pathetically weak, it wins at large scales because it just keeps adding up. Einstein looked at this and thought, there must be a connection. There must be some reason why these two forces, which seem so similar mathematically, behave so differently. He thought maybe gravity was a consequence of the geometry of space itself, which it is. Space curves near mass, and objects follow the curved paths. That was general relativity, and it worked beautifully. But electromagnetism, that didn't fit into the geometry picture the same way. He tried to force it in, tried to find a unified field theory that would make both forces emerge from pure geometry. He worked on it for decades. He never got it. Now here's where it gets really strange. It's not that Einstein was wrong to try. It's that nature might actually be telling us something fundamental. These forces are not the same kind of thing. Gravity acts on mass and energy. Electromagnetism acts on charge. And there's no known reason why charge and mass should be related at all. They're independent properties. An electron has charge and mass. A photon has energy but no charge, so it responds to gravity but not to electric fields. A neutrino has mass but almost no interaction with anything. Different particles carry different properties, and different forces respond to different properties. But that just pushes the question back. Why do these properties exist at all? Why does the universe have multiple fundamental forces instead of just one? You could imagine a universe with only gravity, or only electromagnetism, or some completely different force we've never seen. But our universe has four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Why four? Why not one? Why not 100? Nobody knows. Einstein's dream was that if you looked deep enough, you'd find that all these forces were really the same force, just appearing different in different circumstances. Like how electricity and magnetism turned out to be the same thing, unified by Maxwell into electromagnetism. Maybe gravity and electromagnetism would unify if you understood them deeply enough. He thought the answer would be beautiful, simple, inevitable. But nature didn't cooperate. The unification he wanted doesn't seem to exist, at least not in the way he imagined. Now, let me tell you how I think about this problem, because it's different from how Einstein thought about it. Einstein wanted unity. He wanted to show that everything came from one beautiful principle. I'm more comfortable with the idea that nature might just be complicated, that there might be several different ingredients, several different forces, and you have to accept them as fundamental. You can't always explain everything in terms of something simpler. Eventually, you hit bottom. You find the basic rules, and you can't go deeper. Take electromagnetism. What is the electromagnetic force? It's a force that acts between charged particles across distance. You can describe it mathematically. You can predict what it will do, but you can't explain it in terms of springs or ropes or anything more familiar, because springs and ropes are made of electromagnetic forces. The electromagnetic force is fundamental. It's one of the ingredients of reality. You have to accept it and build your understanding on top of it. Same with gravity. It curbs space-time. Why? Because that's what mass and energy do. It's fundamental. Einstein didn't like that answer. He thought there had to be a reason, and maybe he was right. Maybe there is a deeper level we haven't discovered yet. Maybe at scales far smaller than we can probe, or energies far higher than we can reach. Gravity and electromagnetism do unify into something simpler. That's what string theory tries to do, what quantum gravity tries to do, but we don't know yet. We don't have experimental evidence. We're guessing. And here's the thing that should make you uncomfortable. Even if we do find a unified theory, it won't answer the question why. It will just push it back. You'll have a new theory that explains gravity and electromagnetism in terms of something else, some deeper structure. But then you'll ask, why does that deeper structure exist? Why does it have the properties it has? And you won't have an answer. You'll just have a new set of fundamental rules. At some point, you have to stop. You have to say, this is just how nature is. Let me give you an example of where this hits you in the face. Quantum mechanics. In quantum mechanics, you can't predict exactly what a particle will do. You can only calculate probabilities. An electron doesn't have a definite position until you measure it. It's in a superposition, a combination of many possible positions at once. Why? There's no answer. That's just how quantum mechanics works. You can write down the equations, you can make predictions, and the predictions match experiments perfectly. But you can't explain why nature behaves this way. It's fundamental. Einstein hated that. He thought there must be hidden variables, some deeper level of reality where things are deterministic and particles really do have definite position. He spent years trying to prove that quantum mechanics was incomplete. He lost that argument. Experiments showed that quantum mechanics is correct and there are no hidden variables. Nature really is probabilistic at the fundamental level. Einstein had to accept it, or at least live with it, even though he never liked it. So here's the question Einstein couldn't answer, stated clearly. Why are there multiple fundamental forces with wildly different strengths and no obvious connection between them? And the answer might be, there is no why. That's just the universe we live in. The forces exist, they have the strengths they have, and there's no deeper reason. Or maybe there is a reason, but we haven't found it yet, and maybe we never will. Either way, you have to be comfortable with not knowing. Now, let's think about what this means for how you understand the world. Most people want explanations to go on forever. You ask why, and you get an answer. And you ask why again, and you get another answer. But in physics, that process has to end somewhere. You reach the fundamental laws, and you can't ask why anymore. You can only ask what and how. What does the electromagnetic force do? How does gravity curve space-time? Those questions have answers. Why do they exist? That might not have an answer, and that's okay. In fact, that's the only way physics can work. If every explanation required a deeper explanation, you'd never get anywhere. You'd have infinite regress. Instead, you find the fundamental rules, you test them against experiments, and you build your understanding of everything else on top of them. Those fundamental rules might be arbitrary. They might be different in other universes, if other universes exist. But in our universe, they're fixed. That's the reality we have to work with. Einstein wanted more. He wanted to show that the fundamental rules weren't arbitrary, that they were necessary, that they had to be the way they are because of some deeper principle of beauty or symmetry or logic. And maybe he was right. Maybe there is such a principle, but we haven't found it. And in the meantime, we have to do physics with the rules we've got. We have to accept that gravity is weak, electromagnetism is strong, and we don't know why. That's not a failure. That's just honesty. Let me tell you something about imagination that's relevant here. When you're trying to understand nature, you have to be willing to imagine things that seem impossible or absurd. Curved space-time seemed absurd. Quantum superposition seemed absurd, but they turned out to be true. So maybe the unification Einstein wanted is possible, but it requires imagining something completely new, something that doesn't fit into our current framework. Or maybe it's not possible, and nature really is fundamentally disunified. Either way, you have to follow the evidence, not your preferences. Here's the hard part. The evidence we have suggests that gravity and electromagnetism really are different. They don't unify in general relativity. They don't unify in quantum field theory. Every attempt to force them together runs into mathematical problems or conflicts with experiments. So either we're missing something huge or they're genuinely separate. And if they're separate, then Einstein's question doesn't have the answer he wanted. It has the answer, they're just different forces. But think about what that means. If the fundamental forces are arbitrary, if there's no reason they have the strength they have, then our universe is one possibility among many. In another universe, gravity might be stronger. Electromagnetism might be weaker. The strong force might not exist. And life as we know it couldn't exist in those universes because the forces wouldn't balance out the right way to make stable atoms, stable stars, stable planets. We live in a universe where the forces happen to have values that allow complexity. Is that luck, design, coincidence? Nobody knows. This is where physics touches philosophy. You can calculate the properties of the universe, given the fundamental forces, but you can't calculate why the forces have the values they do. That question might be outside the scope of physics entirely. It might be a question about the nature of existence itself, not just the nature of physical law. And if that's true, then Einstein's question wasn't just unanswered by him. It might be unanswerable by anyone using the tools of science. Now, does that bother you? It should. It bothered Einstein. It bothers me. But it's also liberating in a way. It means reality is deeper than we thought. It means there are questions we can't answer yet, and maybe never will. That keeps physics alive. If we knew everything, if we had the final theory of everything, physics would be over. But we don't. We're still exploring. We're still finding new questions, and some of those questions might not have answers. Let me give you one more way to think about this. Suppose you find a rock sitting in a field. You ask, why is this rock here? You can answer that. It rolled down from the mountain. Why did it roll? Gravity. Why does gravity pull things down? Because mass curves space-time. Why does mass curve space-time? Because that's what the Einstein field equations say. Why do the Einstein field equations hold? Because that's the structure of general relativity. Why does general relativity describe our universe? There you stop. That's a fundamental law. You can't go deeper. Einstein wanted to go deeper. He wanted to ask, why does general relativity have the form it has? And he thought the answer might involve unifying it with electromagnetism. But that unification didn't work. So either there's a different unification we haven't found, or the question, why does general relativity have the form it has, doesn't have an answer. It's just a brute fact about our universe. And if that's true, then Einstein's question was a dead end. Not because he was wrong to ask it, but because nature doesn't provide the kind of answer he wanted. Here's the deepest thing. The universe doesn't owe us an explanation. It doesn't have to make sense to us. It doesn't have to be unified or beautiful or simple. It just has to be consistent with itself. And as far as we can tell, it is. The laws of physics work. They make predictions. Those predictions match experiments. That's all we can ask for. If the laws seem arbitrary or disconnected, that's our problem, not nature's problem. So where does that leave us? Einstein couldn't answer why gravity and electromagnetism are so different. We still can't answer it. Maybe someday someone will. Maybe they'll find a deeper theory that unifies everything. Or maybe they won't. Maybe the question doesn't have an answer. Either way, we keep doing physics. We keep asking questions. We keep testing nature. We keep trying to understand. Not because we're guaranteed to succeed, but because that's what curiosity demands. And that's the real lesson here. Einstein was one of the greatest physicists who ever lived, but he didn't have all the answers. Nobody does. The universe is full of mysteries. Some of them we'll solve, some of them might be unsolvable. But the process of trying to solve them, the process of pushing against the boundaries of knowledge, that's what makes physics worth doing. Even when you fail, you learn something about the limits of understanding. And sometimes the limits are just as interesting as the answers. So the next time someone tells you they've figured out the final theory of everything, be skeptical. Einstein couldn't do it. Nobody since has done it. Maybe it's impossible. Maybe the universe is fundamentally messy, fundamentally disunified, fundamentally beyond our ability to reduce to one simple principle. And if that's true, then the most honest thing we can do is admit it. Not knowing is okay. Not being able to know might be okay too. What's not okay is pretending we know when we don't. Einstein spent the last decades of his life chasing a unified theory. He didn't find it. Some people say he wasted his time. I don't think so. He was asking the right question. He was pushing against the limits. He was trying to see if nature had one more secret to reveal. It didn't, at least not to him. But the effort mattered. The questioning mattered. And the fact that he failed tells us something important about the universe. It tells us that unification isn't easy. It might not even be possible. And that's a piece of knowledge, too. So here's where we are. We have four fundamental forces. They don't obviously unify. They have wildly different strengths for no apparent reason. Einstein wanted to explain why. He couldn't. We still can't. Maybe we never will. But we keep trying, because that's what it means to do physics. You don't stop at I don't know. You ask how you might find out. You think about what experiments would test your ideas. You follow the math where it leads. And if it leads nowhere, you try something else. That's the process. That's the game. And in the end, that's Feynman's way of thinking, not Einstein's way. Einstein wanted beauty and unity. I want truth. If the truth is messy, fine. If the truth is that there are multiple fundamental forces with no connection, fine. I'll accept that if experiments say so. I won't force nature into a framework it doesn't fit. I'll let nature tell me how it works, not the other way around. And right now, nature is telling us that Einstein's question might not have the answer he wanted. That's uncomfortable. But discomfort is where understanding begins.